Not every privileged credential is a password. SSH keys, tokens, certificates, and cloud secrets can unlock critical systems quietly. In this topic, we'll look at why these credentials matter, where they create risk, and how strong management keeps privileged access under control. You've already built the PAM foundation: who privileged users are, why attackers target them, and how vaulting, rotation, session monitoring, and pause reduce risk. Now we widen the lens. Privileged access also exists in SSH keys, API tokens, certificates, and cloud secrets, and they require the same discipline. Privileged access is not limited to someone typing an admin password. Many environments grant the same power through secrets embedded in code, configuration files, automation pipelines, and cloud services. An SSH key can log directly into a server. An API token can allow a script to change production data. A certificate or cloud key can authenticate a workload across systems. That is why PAM must treat these secrets as privileged credentials. If one is stolen, an attacker may bypass normal login controls and reach critical infrastructure without ever knowing a user's password. SSH key authentication works as a trust relationship. The private key stays with the user, admin workstation, or automation host, and proves identity during login. The matching public key is copied to the server, often in authorized keys, where it acts like an approval record. If the private key is stolen, an attacker can become that identity, so protection and rotation are critical. Just as important, every trusted public key needs context: who owns it, where it grants access, why it exists, and what level of privilege it enables. The risk with SSH keys often starts when no one can answer basic questions: which keys exist, who owns them, and what systems they reach. Orphaned keys keep access alive after people leave or applications disappear. Shared private keys make actions difficult to attribute. Overprivileged keys may allow root or broad server access for years without rotation. For attackers, these are hidden privileged pathways. For defenders, they create blind spots: hard inventory, unclear ownership, unseen access, and slow revocation when something goes wrong. Governance starts with visibility. First, scan the places SSH keys hide: servers, endpoints, code repositories, automation scripts, and configuration files. Then enrich each finding with context: who owns it? Which system uses it? What account does it access? Is it production or non-production? And what business process depends on it? That mapping turns raw key material into accountable access. From there, risk becomes easier to see: duplicated keys, root access, stale keys, and orphaned keys. The goal is a centralized inventory that PAM teams can review, rotate, revoke, and audit. SSH keys need the same lifecycle discipline as privileged accounts. Start with ownership. Every key should have an approved requester, business justification, naming standard, and defined scope. Once provisioned, limit what the key can do using least privilege, source IP restrictions, forced commands, or short-lived certificates. Monitoring closes the loop by spotting unusual access and triggering review. Rotation should be routine and immediate after compromise, role changes, or departures. When access is no longer justified, revoke quickly by removing the public key from systems and disabling related accounts. Orphaned keys are silent backdoors. A secret is any credential that lets software prove who it is and what it can access. In modern systems, secrets appear in several forms: application credentials like API keys, OAuth tokens, passwords, and connection strings; infrastructure credentials like SSH keys, certificates, private keys, and encryption keys; and delivery platform credentials like Kubernetes secrets, CI/CD tokens, registry logins, and webhooks. The key is not just naming them. It is judging each secret by lifespan, privilege, exposure risk, and how difficult it is to rotate. That tells you where stronger controls are needed first. Most secret incidents follow a familiar pattern. A developer places an API key in code, a script, an image, or a config file. That material then moves through repositories, build systems, logs, tickets, backups, or chat tools where access is broader than expected. If the secret is long-lived and overprivileged, an attacker can use it to reach cloud resources, copy data, or disrupt services. The worst failures are quiet: no monitoring, no alerting, and no rotation after exposure. Prevention means treating every secret as temporary, tightly scoped, traceable, and easy to revoke. Secure secret storage is a controlled retrieval process, not just a place to hide values. Applications, users, cloud services, and automation should authenticate first, then receive only the secrets or cryptographic operations they are allowed to use. A secrets vault is best for centralizing passwords, tokens, rotation, and audit trails. KMS is best for managing encryption keys that cloud services use directly. HSMs add tamper-resistant hardware protection when assurance requirements are highest. What you want to avoid is unmanaged storage. Files, repositories, environment variables, or scripts where secrets can spread silently. Treat every secret as a managed asset, not a one-time string. The lifecycle begins with secure creation, strong entropy, approved generators, and consistent naming, so ownership is clear. Next, store the secret in a central vault and let applications retrieve it only through authenticated identities with least privilege. From there, secrets should rotate or expire automatically based on schedule, usage, or risk. When a system is retired or access is no longer justified, revoke the secret immediately. Throughout the lifecycle, keep audit records so teams can investigate misuse, prove compliance, and improve the process. Instead of placing a database password in code or a config file, the application first proves its identity to the vault. That identity might come from the cloud platform, a certificate, or a short-lived token. The vault verifies the request, creates a temporary credential, and returns it only when needed. The application uses that credential to connect, and then the credential expires automatically. This removes long-lived secrets from code, limits standing privilege, and makes access easier to audit and revoke in a zero-trust model. In cloud-native delivery, secrets move quickly. A developer may trigger code that reaches a repository, a CI/CD platform, a container registry, and finally, Kubernetes or a cloud runtime. At each step, credentials can appear: IAM keys, service principals, pipeline tokens, deployment keys, artifact credentials, and signing certificates. The risk is not only where secrets are stored. They can leak through commits, build logs, variables, images, and overly broad runtime permissions. Strong programs encrypt Kubernetes secrets, enforce RBAC, connect to external secret managers, scan continuously, apply policy as code, and rotate automatically. An effective secrets program is more than a vault rollout. It is a PAM operating model for every credential that can create privileged access. Start by defining ownership, classification, approvals, access controls, rotation expectations, and emergency revocation. Then connect the program to the systems that actually use secrets: IAM, PAM vaults, SIM, ticketing, CI/CD, cloud IAM, and endpoints. Measure progress with practical indicators such as unmanaged secrets, rotation compliance, orphaned SSH keys, and privileged secret access events. Finally, make the work repeatable. Onboard applications, review access, respond to leaks, and produce compliance evidence without heroic effort. SSH keys and secrets are privileged credentials, and they need full lifecycle control. Unmanaged, shared, stale, or overprivileged access creates hidden risk. Strong PAM programs discover secrets, store them securely, enforce least privilege, rotate and revoke access, monitor use, and keep audit evidence. Next, we connect these controls to compliance, governance, reporting, and audit readiness.